Hi, chemistry. We are going to talk today about the mole. Finally, we've heard so much about it. It's been this term floating in the background of chemistry. It's the famous thing we talk about chemistry. We're finally going to talk about it today. So, the mole is really a fairly simple concept, but it's hard to keep this concept in the front of our mind. So, we're going to start by talking about this concept of the mole. And it really centers around donuts, which life should in general, right? It should just center around donuts. But it actually centers around how we count donuts. So if you are a baker and you are in the process of baking a lot of donuts, you're not going to count donuts out one by one, right? If somebody comes and says, okay, you are the best donut baker in the world, and I want to send your donuts all over the country. So let's pack this whole plane full of donuts. And you say, right on it. Let's do that. Here's one donut. And here's two donuts. And here's three donuts. You're not going to do that. It's too slow, right? If you have to pack a whole plane full of donuts, you're probably going to count in terms of boxes of donuts, right? Or maybe cases of donuts. Or maybe forklift loads of donuts. You're not going to count donuts one by one by one. It's too slow. And the numbers get too bulky. So usually when you count something that is baked, or even some things that are not baked, you count them in dozens. So 1 dozen, that term, 1 dozen, is a way of counting in groups of 12. In fact, we count a lot of things this way. Paper, for example, we count papers in reams. 1 ream of paper is 500 sheets. Our high school, for example, buys a lot of paper. So our high school goes to our paper seller, and what they don't say is, I want 1,294,000 sheets of paper, please. What they're going to say is, I want 500 reams of paper, right? Or maybe a case. 1 case. I actually don't know how many pieces of paper in a case. Probably 200. Let's say 200 sheets. Right? So we do this with a lot of things. Instead of counting individual numbers, we count them in groups. And that's exactly what a mole is. It's a group of particles. And we count them all together because counting them individually is just too small. It's tough to count individual atoms or individual molecules or individual ions, right? And the numbers just get way too bulky. And so we count them in groups. And that group we call a mole. And 1 mole of particles is going to be a group of atoms. Now, it's a really, really big group of atoms. It's 6.02 times 10 to the 23rd particles. Now, I say particles because particles can be anything, and that's true for all of these. If we're talking about particles in terms of chemistry, we can talk in terms of elements, like you see on the board. You can see zinc, carbon, magnesium, copper, right? We can talk in terms of elements. We can talk in terms of atoms. We could talk in terms of molecules or ions or compounds. We can talk in terms of a lot of different particles, right? One particle, one piece is not always the same. And this is true for other things too. If we go back to a dozen, I can have a dozen donuts. I can have a dozen bagels. I can have a dozen muffins. They don't always have to be the same thing, right? I can have a dozen elephants. I can have a dozen marbles. I can have a dozen of anything. Well, the same thing is the mole, because the mole is just a group of particles or a group of things. I could have a mole of donuts. I mean, I couldn't actually have a mole of donuts because that'd be a lot of donuts. But theoretically, I could talk about a mole of donuts or a mole of elephants or a mole of marbles or a mole of sheets of paper. It's just referring to a group. Now, I want to take a minute and think about this real fast in terms of comparing and contrasting them. So if I have 1 dozen donuts, I'll just draw a donut, and 1 dozen elephants. Let's see, elephants are not so easy to draw. Give it a big ear, then it totally looks like an elephant, right? Kind of. Okay, anyway, what I want you to pause the video here and think. What is one thing your group of donuts and your group of elephants have in common? And what's one thing that would be different about the group of donuts and the group of elephants? Pause here and see if you can come up with one thing for each. Now, there's a ton of things you could come up with, but probably your similarity is going to be the number of things, right? Your differences are going to be that a thing, in this case, is elephants, and a thing, in this case, is a donut. Another difference is going to be the weight. The weight is going to be heavy. If you have a dozen elephants, the weight of a dozen donuts is not so heavy. Also, the space they take up, right? A dozen elephants takes up a lot of space. A dozen donuts takes up a box of space, right? So their volume is going to be different. So there's definitely differences between a dozen donuts and a dozen elephants, but the number of things you're talking about is still the same. The same thing is true if we're talking about a mole. If we have a mole of zinc and a mole of carbon, there's going to be some differences, right? The number of atoms present, the number of things present is going to be the same, right? But things in this case is, in one side is zinc, in the other side it's carbon. They're going to weigh different amounts because an atom of zinc is not equal to an atom of carbon. So they'll probably weigh different amounts. They'll probably take up a different amount of space. You can even see here that, a mole of carbon is not so big. A mole of tin is a lot bigger, right? So you can see that there's definitely differences, but the number of things we're talking about is still the same. Same thing if we are comparing, let's say, 1 mole of sucrose. Actually, let's do glucose, C6H12O6, and 1 mole of carbon. So you can have a mole of a molecule, you can have a mole of an atom, right? The number of things is still going to be the same. You're still going to have 6.02 times 10 to the 23rd things, but things on one side will be carbon atoms. Things on the other side will be glucose molecules. Their mass is going to be different. The space they take up is going to be different. but the number of things contained in both groups is the same. So this is really the concept you have to embrace, that the idea of the mole is a counted group. It's a group of things that have a very specific number of those things inside. Okay, so now let's look at this from kind of a historical perspective, because doing that gives us a little bit of information. So the number that we're talking about here, 6.02 times 10 to the 23rd things, could be atoms. I like the term things better because it helps you remember it could be atoms, could be molecules, compounds, ions, could be a whole bunch of things, right? So this number is attributed to a guy named Avogadro. He actually didn't come up with this number, but the number was based off of some experiments he did and some conclusions that he made. So he gets his name on the number. And the less historical version of it, of how it came up, is based on the isotope carbon-12. And this is because numbers, when you're looking at carbon-12, work out very nicely. So remember, carbon-12 is a specific isotope of carbon. It's going to have 6 protons. It's going to have 6 neutrons. It's going to have 6 electrons flying around, right? It's a very specific atom. Well, if you have 12 grams of carbon-12, then you have Avogadro's number of atoms, 6.02 times 10 to the 23rd carbon-12 atoms. And that specific group with that specific number in it, remember, is called 1 mole of carbon-12 atoms. So notice what we have here. We have equivalent statements here. Notice that 12 grams of carbon-12 is equal to a specific number. That's an equivalent statement. We can actually use that as a conversion factor. Remember, conversion factors have 2 units, grams, atoms. And the top of the equivalence statement, or conversion factor, is equal to the bottom of the conversion factor, right? If you have 12 grams of carbon-12, you have 6.02 times 10 to the 23rd atoms of carbon-12. The top is equal to the bottom, and therefore you can use that because that fraction is equivalent to 1. The top and the bottom are equal. It's equivalent to 1. You can use that to convert in and out of grams and atoms. Same thing with atoms and moles, right? They are also equal. Top is equal to the bottom, 2 units. You can use it to convert in and out of atoms and moles. And notice also that this is from the periodic table, which has some implications that we're going to look at in just a second. So you can use this as a conversion factor. If you have 1 mole of carbon, you have 12 grams of carbon. That's a conversion factor that you can use to convert in and out of grams and moles. You could also have 1 mole of carbon equal to 6.02 times 10 to the 23rd carbon atoms. That's a conversion factor that you can use to convert in and out of moles and atoms. So this is why the mole becomes so important, because it's easy for us to use this group to count quantities that we have of atoms or ions or particles, right? Counting individual water molecules is really difficult. Counting out a mole of water molecules is something we can do in a graduated cylinder. It becomes really easy to count things in terms of moles because finally we have this group of molecules that we can see and hold. It's on the macroscopic level. So it becomes really convenient for us to work in terms of moles instead of working in terms of atoms. But we also know how they are related, and therefore we can convert in and out of them. If it's convenient for us to measure in terms of moles, that's great. We can measure in terms of moles. But if the answer we want is in terms of atoms, that's great too. We can convert into atoms. We can measure in moles and convert into atoms. It's all very convenient. So this is why the mole becomes such a big deal for us as chemists. So let's just finish up today by talking about this idea of how much 1 mole weighs. Now that's what we call molar mass. Right? How much does 1 mole weigh? So the mass of 1 mole is called molar mass. And we talked about that already for carbon. So here's carbon on the periodic table, and look right below it, right? The mass of 1 atom of carbon is 12.01 AMUs. Well, if you have 6.02 times 10 to the 23rd atoms of carbon, right? Instead of talking about all those individual carbon atoms, we're going to talk about them as a group. I have 1 mole of carbon. Well, check this magic out. 1 mole of carbon weighs 12.01 grams. It's magical, right? That mass that's listed on the periodic table without a unit is listed without a unit on purpose, because that mass, if you're talking about that mass in terms of grams, then you are talking about 1 mole of that atom. If you're talking about that mass in terms of AMUs, well, you're talking about 1 atom of carbon, right? So this number has a dual purpose. You can put 2 different units on it and talk about 2 different quantities. Pretty tricky, huh? It's kind of nice, kind of convenient. So if I ask you, how much does 1 mole of hydrogen weigh? Normally you would be like, Martins, I don't know. I've never measured that out. Well, you don't have to. You have the periodic table right here. Chana, 1.007. Actually, I guess that should be an 8. We'll cut it off after the 7 and round up. 1.008 grams of hydrogen. If you have 1.008 grams of hydrogen, you have a mole of hydrogen. You contain 6.02 times 10 to the 23rd atoms of hydrogen. Or if you have 1 mole of hydrogen gas, molecular hydrogen, right? We're just going to multiply that by 2. Hydrogen plus hydrogen, 2.016 grams of H2. I have a mole of hydrogen molecules. All of this information you can get off the periodic table. The molar mass of atoms, the molar mass of molecules. You can start adding them together and building your own molecules or polyatomic ions. And it's all contained in this fabulous tool that we've been talking about this whole year called the periodic table. Like I said, as you get to know it and you start to unpack it, it just contains so much information. So this mole is really convenient for us to measure. It's really convenient for us to talk about, and it's really convenient for us to weigh because all this information is contained in the periodic table. And we get back to what we were talking about in the beginning. If we want to compare 2 different things, 1 mole of carbon and 1 mole of hydrogen, and we want to talk about how they're similar and different, remember, they're similar because the number of compounds, the number of atoms is the same for both. it's still that same group of atoms, but the weight is going to be different, or the mass is going to be different. A mole of carbon is 12.01 grams. A mole of hydrogen is 1.008 grams. Just like the mass of a dozen donuts and the mass of a dozen elephants will be different, the counted number is the same, the mass is different. It's true for elements as well. The mass of the elements are going to be different. The counted number is the same when you're talking about 1 mole. Okay, so that's kind of the concept of the mole. We're going to start working with that. When it gets confusing, come back to this idea that a mole is just a group of atoms. It's a convenient group with a specific number of particles in it, and we just count in groups. Come back to this concept, and your context will make more sense. So let me know what questions you have right now. We will practice this together. I will see you in class.